Hi 253. This is the first of two videos to discuss a new technique for integration called trig substitution. This is section 7.3 from your text. So to give us a little bit of motivation as to why we want to think about this new technique of trig substitution, it may be helpful to think about an integral where we may encounter an expression that would be good for performing a trig substitution on. So just to mock up an example for a second, I know there's a much easier way to solve this problem, but for example, we might want to calculate the area enclosed by a circle, for example, in the first quadrant here. So remember that with the circle of radius a, we're able to explicitly write the top half of the equation of the circle as this here listed. So y equals the positive square root of a squared minus x squared. Again, that's the explicit form for the top half of a circle of radius a centered at the origin. So if we wanted to, for example, calculate the area of this section of the unit circle, that would be writing the following definite integral. So we would say we would do the integral from 0 to a for x, right, dx here, and the integrand would be the function bounded above, so the square root of a squared minus x squared. Now the problem with this is that this integrand here, we don't have any techniques to actually figure out its antiderivative. A u substitution is not going to work because of the squared x here, but the lack of an x outside of the radical, and we can't do integration by parts. So a new technique will enable us to figure out how to handle an integral of this form. So let's start out with an easier example first, and maybe let's start out with a motivation for what kind of substitution we'll make. So in general, this technique of a trig substitution is going to be useful for integrating functions where there is an expression of one of the following forms. Either you have an a squared plus x squared or an a squared minus x squared, or you've got x squared minus a squared. So any of these three forms here, if they're in the integrand, then a trig substitution might be the way to go. Again, you'll have to pay attention to whether a u substitution might be more useful or not. Or an integration by parts maybe. But let's check out and see what happens first in one of these three situations and what kind of substitution we'll make. So let's first consider when we are looking at a squared minus x squared. If we have this kind of an expression in our integrand, and we aren't able to do a u substitution or an integration by parts or something like that. So for when we have a form like this existing and we can't do any of those other options, it may be beneficial to do the following substitution. Let's let x equal a sine theta, and let's see why that might be a good choice. Why would that be a good choice? It simplifies this expression significantly. So notice it takes an expression where there's a difference like this, and if we replace x squared, we get a squared minus a squared sine squared theta. And because of the Pythagorean identity, if you factor in a squared from each term, that would be a squared times 1 minus sine squared theta. The Pythagorean identity tells us that's a squared cosine squared theta. So notice we just took an expression that had a difference in it and transformed it into an expression that now only makes use of multiplication. This is nice because now anytime this expression occurs under a radical or raised to a power of some kind, now that exponent can work across the multiplication instead of being stuck not being able to work across the addition or subtraction. So let's consider an example. Let's try this with an example specifically. So let's see if we can figure out the integral or figure out what the value of this definite integral should be. So let me get a... So notice here in the denominator that we actually have a form just like we were talking about. We have an a squared minus x squared here, yes? So in this case we have a is going to be 3, right? So we have a is 3. And in this case then what that means is that we can make the following substitution. We can let x equal a sine theta, and I'm sorry for the little connector on the equal sign. I'll try to improve that as we move along. So we need to do a sine theta. So we're going to do 3 sine theta. Okay, so if x is equal to 3 sine theta, then remember we're going to be able to transform the x's that appear in this definite integral into their equivalents in terms of theta. We'll also have to change the limits of integration here. Okay, so if x is equal to 3 sine theta, then what is dx equal to? So dx is going to be equal to what? The derivative of 3 sine theta, which is 3 cosine theta, d theta. Okay, so now let's go about replacing all the parts here. Here's the definite integral. Dx is going to be 3 cosine theta d theta all over. Now what happened when we replaced, you remember what happened with the a squared minus x squared? A squared minus x squared turned into a very special expression. Remember that was a squared cosine squared theta when we made this substitution? So that means this inside part down here, you can work it out again if you like, but we know that it's going to turn into what? It's going to be 9 cosine squared theta. That's this inside stuff because of what we just did on the previous slide, and that's going to be raised to the 3/2 power. Now we also have this issue of needing to change the limits of integration because we have performed a substitution. Okay, and the limits of integration must be changed when you do a substitution, or you can remember to change them back at the end, but at this point I think it's better just to change them. So let's go about changing the limits. So what happens now when x is equal to 0? Well, it may be good to think about the fact that our x and theta are related via this relationship here. X is equal to 3 sine theta. So because x is equal to 3 sine theta, notice that that means x over 3 is equal to sine theta. Yes? Which means also then that theta is equal to what? Sine inverse of x over 3. And this is good because we know a value of x, we're trying to get an angle of theta out of that, right? We're trying to actually figure out what theta needs to be when we know x. This is important with one sort of attentive point we need to pay attention to here. Remember that the sine inverse here is only defined on a certain interval because inverse trig functions have a specified domain. Remember that the requirement here is that x is defined on the following interval. Is it x that's defined on the interval, or is it the angle? It's actually the angle that's defined on the interval, remember. The reason for that is you have to define an angle interval so that sine is 1 to 1, so that the inverse even exists, right? So remember we had to restrict the angle of theta so that sine is 1 to 1, which means that the angle that can be output by sine inverse has to be between these two values of theta here, negative pi over 2 and pi over 2. Okay, so let's go about changing the limits of integration. If x is equal to 0, well then what are we really trying to say? We're really trying to say when is 0 over 3 equal to sine of theta on this interval for theta, right? So when does sine of theta equal 0 on this interval? Well, isn't that when theta is equal to 0? Right? So that's going to change our lower limit. So that's not the same 0. Remember, that's 0 for theta, right? And the reason we get that is because we're wondering when does sine of theta equal 0 in this interval. That's when theta is equal to 0. Okay, let's do the other limit of integration. So here we're wondering about when x is 3/2, then we have 3/2 over 3 equal to sine of theta. Okay, again, you can interpret that as sine inverse of that expression equals the angle measurement theta. So really this boils down to when does sine of theta equal 1/2? Again, on this specified interval. And remember, if you're remembering your unit circle and everything on that interval, that turns out to be theta is pi over 6. So that's going to be our new upper limit of integration, pi over 6. Okay, now we can continue on and try to work with this definite integral here. It looks like we've got some work with some exponents here to simplify things. So let's see, let's work with the denominator. So 3 cosine theta d theta over, let's work the exponent, 9 to the 3/2. So that means take the square root of 9 and cube it, which is 27. If you need to pause the video, remember you can check that. Cosine squared to the 3/2, remember you multiply those two exponents, which means we're left with cosine to the 3rd theta. And we actually can do a little bit of simplifying here. So 0 pi over 6. So it looks like we've got 3 and 27, that could be brought out front as a 1/9, and cosine over cosine cubed is 1 over cosine squared, theta d theta. But remember, 1 over cosine squared, that's actually what? That's secant squared. And now the task just comes down to figuring out the antiderivative. So what's the antiderivative of secant squared? Well, don't forget, that is tangent squared. Nope, not tangent squared, just tangent of theta. Sorry about that. 0 pi over 6. Okay, the derivative of tangent is secant squared, so the antiderivative of secant squared is tangent. So now we're at the point where we need to actually just evaluate the function here. So let's go ahead and use the fundamental theorem of calculus. So we're at tangent pi over 6 minus tangent of 0, with the 1/9 out front, of course, and tangent of pi over 6, that is 1 over the square root of 3, so this is 1/9 times 1 over square root 3, Rationalize the denominator if you must. Tangent of 0 is 0, so I don't need to worry about that part. So here we are left with just that answer. We can actually just finish right there. Okay, so in this way, we kind of worked our way through making use of the relationship between the substitution and the angle. And now what we can do is actually try to work out that example that we had at the beginning with our, let's see, I need my pointer back. Here we go. With our circle here, right? This was, remember, the original area of the quarter of the area of the entire circle. So let's see if we can work this one out quickly so that our video doesn't get too long here. So notice we have a squared minus x squared. Remember, that means that our substitution should be x equals a sine theta, which means dx is a cosine theta d theta. Okay, so let's start making our replacement here. So integral square root of, remember this is going to turn into what? A squared cosine squared theta. And dx is a cosine theta d theta. And now we just have to change our limits of integration. Again, remember we can make use of the same information about sine theta, x equals a sine theta. So that means we can write x over a equals sine theta. Again, I apologize for the equals connecting bar right there. That's not supposed to be there. It's just the pen acting funny. So when x is equal to 0 for this lower limit of integration, when x is equal to 0, we're wondering when on the interval negative pi over 2 to pi over 2, sine is equal to 0. Well, that's again 0, just like in the last example. And now when x is equal to a, we're wondering what? When x is a, you get when is sine of theta equal to 1 on the interval negative pi over 2 to pi over 2. That happens when? Let's see, what happens when sine of theta is 1? Isn't that the very top of the unit circle, right? When the y value on the unit circle is 1, and so that happens at pi over 2. Yes? Okay, so now we're able to continue our work here. Because we're assuming that A is going to be positive according to our unit circle that we are not unit circle, but our circle of radius A that we started out with, and we can say that cosine is going to be positive for the angles that we've considered here because we're considering negative pi over 2 to pi over 2, so the cosine of that angle will always be positive also. Then the square root is going to be simply a cosine theta, no absolute values necessary because the stuff inside is all positive. And now we get what? A squared integral 0 pi over 2 cosine squared theta d theta. And this should look familiar because this is an integral we actually worked on in class where we have an even power acting on a cosine here. So we're able to make use of the half angle formula to say 1 plus cosine 2 theta all over 2 d theta. So we get a squared, and now we have to, actually we can bring the 2 out front too. Integral 1 plus cosine 2 theta d theta, going from 0 to pi over 2. And now let's do the antiderivative. So we've got a theta plus, let's see, that would be sine 2 theta all over 2, going from 0 to pi over 2. Good, excellent. So let's see. We changed the angles already, so we should be able to just go ahead and plug stuff in using the fundamental theorem of calculus, because this is all in terms of theta, correct? Okay, so we've got a squared over 2 times, what have we got, pi over 2 plus sine, now I'm going to plug a pi over 2 in here, right? So that means when I plug a pi over 2 in here, it's 2 times pi over 2, which is pi, all over 2. And then we have to do what? Minus a squared over 2. And then I plug in 0. 0 plus sine of 0. And things should simplify nicely here for us. So let's see. Sine of 0 is 0. So everything over here is gone, right? Everything over here gone. Totally gone. Sine of pi, that's also 0. So that's gone, right? And so what have we got? 1/4. That's a 4. Not a 9. That's a 4. 1/4 pi a squared. And that's exactly what we hoped we would get. 1/4 of the area of the circle, pi r squared. R is a in this case. So as you can see, this process allows us to confirm a lot of our geometrical intuitions and some of our formulas, right? We could then prove the area of the circle using this technique here. So in our next video, we'll talk about the other couple of forms and we'll do a couple examples.